recurrence relation means. It's very, very simple. Instead of being given a definition of what's going on like that, we're told that we start with u1 is 2, and that we can get to the next term in the sequence by multiplying the previous term by 3 and adding 4. So I start with the first term is 2, 3 times 2 is 4, so the next term is going to be 6 plus 4, which is 10. Moving on, 3 times 10 plus 4, the next term would be 34. So with that definition of our sequence, we're asked to prove that this formula, un, is 4 times 3 to the n minus 1 minus 2. So that is what we're trying to prove. The top line is the definition of our sequence. Well, we start in the usual way. We start by looking at the lowest value of n, that's n equals 1. If n is 1, we know that u1 is 2. We're told that. If we look at the formula, we get that u1 is 4 times 3 to the 1 minus 1 is 0 minus 2. 3 to the 0 is 1, 4 times 1 is 4, minus 2 is 2. So we have shown that our formula is true when n equals 1. The next stage, same as always, we assume that the formula is true when n is k. We assume that we can find a number k such that uk is equal to 4 times 3 to the k minus 1 minus 2. That is our assumption. We want to show that this formula works when n is k plus 1. How can we get to k plus 1? Well, if we look right up at the top of the page and put n equal to k, we can see that uk plus 1 is 3 times uk plus 4. So we've got that uk plus 1 is 3 times uk plus 4. But on the line above, we know all about uk, our induction assumption, that is 3 times 4 times 3 to the k minus 1, 3 uk, that is minus 2, plus 4. Let's work that out. If we do 3 times 3 to the k minus 1, we will get 3 to the k. So I've got 4 times 3 to the k. 3 times 2 is 6, so it's minus 6, and then there's plus 4 at the end. 4 times 3, I'm going to write my k as k plus 1 minus 1. Minus 6 plus 4 is minus 2. So we now have written this so that, just give a bit more space, we can see it more easily, except that I left the bracket behind. There it is. So I've now got 3 to the k plus 1 minus 1 minus 2. This is just my formula, 4 times 3 to the n minus 1 minus 2 when n is k plus 1. So I have now shown that my formula is true when n is k plus 1. In other words, we've shown that uk plus 1 is equal to 4 times 3 to the k plus 1 minus 1 minus 2. In other words, the formula is true for n equals k plus 1. All that remains is to add the usual last paragraph. We have shown that the formula is true when n equals 1. and that if the formula is true when n equals k, then it's also true when n equals k plus 1. That means that un is 4 times 3 to the n minus 1 minus 2 is true for all natural numbers n by induction. Notice I keep doing the same. All the red pieces, please, all these red bits, you should be doing yourself. Now we come to another example with just another little wrinkle in it, which we shall have to sort out when we come to it. It's another recurrence relationship, and this one is un plus 2 is 3 times un plus 1 minus 2 times un. So I know the first term, I know the second term. First term is 1, the second term is 3. 3 times 3 is 9, minus 2 times 1 is 7. So my third term will be 7. We can define our recurrence, our sequence, like that with this recurrence relation. And we're asked to prove that this is the formula for the nth term, that the nth term, un, is 2 to the power n minus 1. Well, it's a proof by induction, so let's start off in the usual way. N equals 1. Well, if n equals 1, then we know that u1 is 1. And from the formula, we get u1 is 2 to the power 1 minus 1, which is 1. So we have that the formula is true when n equals 1. It's induction, so let's make an assumption. Assume that we can find k such that the formula is true, uk is equal to 2 to the k minus 1. Okay, let's move on. I lost something. Okay, let's move on. If we use our recurrence relationship, when n is k, then we can write down on the next line that uk plus 2 is equal to 3 uk plus 1 minus 2 uk. So what was all that about? If I want to work out uk plus 2, I have to know uk. Yes, I've assumed that I know uk. But I've also got to know what uk plus 1 is. So at that point, I need to be able to assume that I know what uk plus 1 is. So we need here to say that we can find k and k plus 1, so that uk is 2 to the k minus 1, and uk plus 1 is 2 to the k plus 1 minus 1. So that is what the fuss was about, but I haven't quite finished. We're now going to say, when we come to our induction, if we can find k and k plus 1, we can prove a result for k plus 2. I have to start off with, if I know that it's true for n equals 1, and I know that it's true for n equals 2, then I can show that it's true for n equals 3. I need to put another one in here. So I need n equals 2. If n is 2, then we get u2 is 3, looking at the top line, we know that u2 is 3. It's part of the definition. And from the formula, 2 to the power 2 minus 1. u2 is 2 to the power 2 minus 1, which is 3. So the formula is true when n equals 1 and when n equals 2. Okay, let's get rid of this little bit down here, we hope. And we are back to a clean page. Your book, if you look in your book, with this particular example, they will tell you to start with n equals 1, n equals 2, and n equals 3. That is more than you need. In the previous example, they tell you to start with n equals 1 and n equals 2. You don't need n equals 1 and n equals 2. N equals 1 is enough. So let's go back down to where we were. We've now assumed that our formula is true for 2 values, and so we can carry on. This now gives us 3 uk plus 1, that is 2 to the k plus 1 minus 1. There is uk plus 1, minus 2 uk. uk is just going to be 2 to the k minus 1. And now we do some arithmetic and we hope that things work. We get 3 times 2 to the k plus 1 minus 3 minus 2 times 2 to the k is 2 to the k plus 1. Minus minus is plus. And now if we look at this, we find that we have 3 times this fellow minus 1 of them. 3 of them minus 1 of them is 2 of them. So that is 2 to the k plus 2. 2 times 2 to the k plus 1 minus 1. So this is what the formula would give us if we put n equal to k plus 2. So we've now shown that the formula is true when n equals k plus 2. Now we add the normal paragraph at the end. Let's just get rid of those lines. And we have shown that the formula is true when n equals 1 and when n equals 2. That's the important thing with these. And that if the formula is true when n is k and n is k plus 1, then it will also be true when n is k plus 2. This means that we have shown that un is 2 to the n minus 1 for all positive integers, I should really have said there, n by induction. This then can be found, questions like this and other examples, in your textbook FP1 on pages 130 to 133.